they showed that specific areas of the RNAs don't change, and they showed why. In my, not the splicing and dicing one. Oh, in the episode that I did called The Spaghettification of Irreducible Complexity, I talked about in the middle of that episode how the transfer RNAs that have on the bottom an anticodon, the 3 letters that matches up with the codon in the on the RNA, the anticodon, and then the top they have an amino acid, and they're used in the ribosome to manufacture the proteins. But those transfer RNAs are heavily modified. They're modified sometimes 15, 20 times. So another protein will come and attach to it and change the letters of the RNA or stick something on it. And what Lake et al. Showed was that in the anticodon, you can't change the first 2 letters. The 3rd letter, that's more changeable, because when you have an amino acid that's 4 different codons, it's the 4th one, the wobble base, that can be different. It could be A, C, G, or a T. So if you mutate that one, you keep the same amino acid. But if you change the other ones, you change the amino acid, that's probably bad for the organism. They showed that in the places that get changed on those transfer RNAs, those places are pretty much invariant. Oh, so the cell needs that letter there, so another protein can come and attach to it, make a chemical change to the RNA, or the RNA doesn't function right, and the protein doesn't get made right. So there's a lot of constraint. There's a lot of evolutionary, if you want to call it that, there's a lot of evolutionary design systems, whatever you want to say, constraint. You can't just change anything. Only certain mutations are allowed. Oh, but they also showed that specifically the C to T mutation is by far the most common mutation. In fact, the C to T mutation on the coding strand of the mitochondrial genome, not the opposite, the anti-coding strand, whatever they call it, the strand that doesn't actually code for the RNA and the proteins. No, it's the C to T happens on the coding strand way more often than anything else. So, given billions of years, how come all those C's haven't changed to T's? That's a great question. So, what do we know here? 1, the mitochondria is highly functional. 2, mutations are predictable, which are not supposed to be. 3, it doesn't look like the mitochondrial genome is billions of years old. 4, mitochondrial Eve is a very difficult thing to figure out because it depends upon where in the tree you want to place her. Now, I think she's at the center of the so-called starburst, which is the radiation of all the branches from some central point. I don't think she's on an